So good morning. So these slides of these lectures have already been displayed earlier. So in this particular lecture, we are going to discuss estimation and prediction associated with vector autoregression models. So we have seen in the earlier lectures what is a vector autoregression model, what is the corresponding mean, variance, covariance matrix, cross correlation matrix, etc. And today, and then we also discuss stability, stationarity of such vector autoregression models in the previous lecture. So here today, basically, it is on estimation and prediction. Now, in the estimation, there are generally two, I can say three. One is based on least square, where you have generalized least square and ordinary least square estimators. And then another second type is maximum likelihood. And third type is the Bayesian estimation. However, in your syllabus, we are not getting into the Bayesian aspects, but how we may discuss the least square and maximum likelihood. Okay. Uh, Now, what happens that it is possible that you will see later that under the k-variate multivariate normal assumption of ZT, the maximum likelihood estimates of VRP model are asymptotically equivalent to the least square estimator, which this theory you may be knowing already in the case of regression, multiple regression, etc. So that is exactly going to happen in this case also. So most of the results, we derive or discuss, but some of the results which has got detailed derivations may be omitted for the time being. So let's come to the least square procedure. Now, consider a k-variate VAR-P models. So, suppose you have the data y1, y2, yn is given. Now, since it is P, where P model, the available data with us is actually from P plus 1 to n. Because to write the model itself, we require P observables, see y1, y2, etc. Yt is equal to yt minus 1, yt minus 2, etc., yt minus p. So you are using this p points here. So available data is p plus 1 onwards. This you know already in the case of univariate time series. So exactly that is what happens in this case. So I will be able to write this var p model as yt hat is equal to xt, yt prime is equal to xt prime beta plus zt prime. Now what are these yt prime? Yt prime is nothing but the prime of this. So it is basically yt means yt1, yt2, etc., ytk. So yt prime means you just write in the row vector format because it is on the column vector format. And now xt prime is a new quantity which I am going to define here, and beta is a new quantity which I am going to define here. Zt prime is same as zt, just written as a row vector. This is now, what is this? This quantity which you can see here, we are writing in the form of a regression setup. So if I do that, this xt is nothing but 1 yt minus 1 prime, yt minus 2 prime, etc., yt minus p prime. Remember that each of them are vectors. These are vectors. So I'll be writing 1 yt minus 1 prime, etc., yt minus p prime. That is my xt. And so it is actually, what is the dimension of this? The dimension of this is kp plus 1 dimension, because this has kp rows, and so I will have a kp plus 1 dimensional vector. These are all now row, so so and then you're putting it in the column format. So that's why you have basically each of them is of k, and such p are there, so that is kp, and then there is 1. So that's why kp plus 1 dimensional vector. And this beta, I'm going to put all these bit of phi naught, phi1. Remember that this is a vector. These are matrices, phi 1, phi 2, etc., phi p. So I have beta prime can be written as phi naught, phi 1, etc., phi p is a k by kp plus 1 matrix. So it is a k by kp plus 1 matrix. You can see the order by looking at, because this is a k by 1 vector. So I have only k rows in each of them, but I have p columns in each of them. So there is, I'm sorry, yeah, so because these are sort of diamond, so if you look at here, these are actually k by k matrices. So I have k by k matrices, such p of them are there. So kp, and then there is one here, so kp plus 1 by k by kp plus 1 matrix. So we can write the data. Now, if you write like this, so this is like in a regression, we are writing yi equal to xi prime beta plus epsilon, where xi prime is the vector associated with beta I, I mean the beta I. And then now if I have n observation, we know how to write it as y equal to x beta plus epsilon. So exactly I'm going to do the same thing. So for every t equal to p plus 1 to etc. n, so I have n minus p by k matrix. This is why I'm going to write it as, remember that this is different, different in the sense that in terms of the notation. So now we can write, this is for the, this is just a model still, but here now I'm including the data. So this is exactly like, for example, if you are considering in a regression, so I will have y1, y2, yn, and then I will have x11, x12, etc., x1n, x21, x22, x2n, etc., x n1, sorry, x1p, xnp, and then I will have the corresponding beta p plus epsilon 1, epsilon 2, epsilon n. So this is what in a regression we write it as y equal to x beta plus epsilon. So this is like, y is a n by 1 vector. This is n by p, p by 1, and this is n by 1. Okay, this is what we do in regression. Now I am doing the same thing in the context of time series. So model, when you say this is the model y equal to, so I will have model will have all those beta 1 xi1 plus beta 2 xi2 plus etc. plus beta p xip. Now if you want to increase, now I have not included the 1 here. If you want to include 1, you can have a column with a 1 1 1, so that you consider that I mean, like at the end of each of them, I mean, like you have a constant added to that, so that that constant can be multiplied with that. That 1 can be multiplied with the first component alpha here. So I'll adjust it. So there will be p minus 1 here, and including that there will be p. That's not a big deal. Right. So we'll go back. So this whole thing for the model, and for t equal to p plus 1 to up to n, which is n minus p, so I'll be able to write it as y equal to x beta plus z, where y is n by p by k matrix with the ith row is this, and z is n by p by k matrix with the ith row as zp plus I. So this is what the matrix format. Now why do you want to write like this? Because then the least square theory is very easy. In this case, so once I write like this, if you look at z, z is actually, zt is normal 0 sigma. So zt is, if you can see that your zt, this is 0 is a vector, okay, zt is actually bold, k by 1. So this is k by 1, k by k. Okay, so if I now consider all those zt's in a vector format, look at this zt. So I will have this zt's in a vector format. So that's what this capital Z stands for. Okay, capital means, I mean, this actually everything is capital. So but without this suffix. So it is actually Z is a n by p by k matrix with the ith row as this. Okay, so each row is actually a multivariate normal. Each row follows a multivariate normal. So I can now consider that the entire matrix forms a multivariate normal with the each row, ith row will be a multivariate normal. So this is what we have. So if you look at now, if you see this, what will be the least square theory? Well, actually multivariate normality is not required for least square theory. I'll be simply assuming that it has mean zero and a variance covariance matrix. So sigma. So multivariate normal is not required. If you have multivariate normal, fine. But otherwise, because we are saying that it is a white noise. So normality is an added assumption to that. White noise 0 sigma is enough. So in such a case, what will happen in this case if I want to make it like I? So I'll be multiply by sigma to the power of minus 1/2. So that's the standard trick in multivariate normal distributions. So I will have this as the GLS estimate of sigma. The GLS estimate of beta is given by y minus x beta prime sigma inverse y minus x beta. Uh, Not y minus x beta prime, y minus x beta sigma inverse y minus x beta prime, because the order should match. So I will consider GLS estimate of beta is obtained by minimizing this quantity, which is the trace of this quantity. So now what happens that this is not the usual minimization, because this is a matrix. I mean, like, so you have to be careful about here. So there are some maths involved here, but we just ignore them, because you may have to use this right in the form of Vec and Kronecker product, and then differentiate with respect to this beta uh, for each of these matrices. I mean, like this entire matrix, matrix quadratic form kind of a thing. And then ultimately we can, this proof I am omitting, we get the beta estimate as x prime x inverse x prime y. Perhaps what you would have expected here is x prime x inverse x prime sigma inverse x whole inverse x prime sigma inverse y. That is something which is because of this. So you would have expected something like this. This has the estimate of beta. But surprisingly, due to that Vec and manipulations over there, because this will be the case when you actually consider a simple regression model. For example, if this regression model, and then this is 0 sigma, these are vectors. This is n by 1, n by p, p by 1, and n by 1. Okay, in this case what I will do to make it as independent, or to make it as uncorrelated, I'll be multiplying by sigma inverse y is equal to sigma inverse x beta plus sigma inverse epsilon. So sigma inverse, this will give me a y star is equal to x star beta plus epsilon star. Now the epsilon star is 0i, and I can apply the least square theory. That will give me what will be that? X star prime x star inverse x star y star. This is the estimate. But if you rewrite this x star is nothing but sigma x, and then inverse, and then so here I will get this as, so I'll be considering, I think there is a dash here, so this will give me x prime sigma inverse x whole inverse, and there is a dash here, x prime y, so there is a dash here. Okay, so that will give me x prime sigma inverse, so y. So we may expect like this, okay? But actually what is happening in our case, it's not like that. There is, because there is a, this is for the vectors, what I have talked. Because in this case, X is a matrix, but all others are vector, sigma is a matrix, but these are basically our equation is for the vector n by 1. But here I have a matrix. And when you have a matrix and when you apply least square to that, you may have to convert that into a vec notation. The reason being that most of those theories are available for the vec. So vec means vectorizing. So I may have to vectorize the whole matrix. So that is what I'm skipping that portion. So if you do that exercise, it is possible now that we can show that beta hat turns out to be this. So I'm just presuming this result without the proof. So essentially what this means? This means that your least square theory, even though this is generalized least square, it appears to be like a least square. The reason being that the sigma is vanishing. The sigma inverse is not present here in these two expressions. So this beta hat is basically, this is the least square estimate or generalized least square estimate, because actually we are not ignoring purposefully, it is getting cancelled. So this is what beta hat is, this is the estimate. Okay, so this is the one notable point, this is free from sigma. Now it is possible to obtain GLS estimate over P model equation by equation. That is, one can consider the k multiple linear regressions of YIT on XT separately, where I equal to 1 to a k. So this estimation method is convenient when one considers the parameter constraints in a var P model. Now what happens in the case of OLS? OLS means ordinary least square. So in the ordinary least square, the difference is that instead of minimizing this, I'll minimize this with the sigma replaced with I. So I'll minimize this quantity. And that's what the ordinary least square is all about. So I sort of assume that your Z is normal 0 sigma, but instead of that, it will be normal 0 I. Okay, so replacing sigma by I in the objective function, you get the ordinary least square, the trace, I mean this as the equation. So minimizing this with respect to beta results the same as this. So you get the same thing in the case of OLS as well. Now, you know that how to estimate the errors in the context of least square theory. You will be simply considering y minus x beta hat into y minus x beta hat prime, because that will give the estimate of the variance covariance matrix. So exactly the same thing, I'll be considering zt hat prime, and this running from t equal to p plus 1 to n, and you divide by 1 by n minus kp plus k plus 1 p plus 1, and minus of the entire thing, so there will be this plus become minus over here. So you get this particular thing as the sigma hat as this. What is sigma hat? Sigma hat is nothing but the variance covariance matrix of zt. Okay, so sigma hat can be, so it is like, you have, it's a variance covariance estimator which is sigma. So the instead of the so for a given set of observation, how you get the sample variance covariance matrix. So that's what exactly this is. We are not using the entire thing because of the fact, I mean, the some degrees of freedom is lost because you are estimating the mean part of that. So this will be simply n minus k plus 1 p minus 1. Now it's not difficult to show that expected value of beta hat equal to beta. So you look at this, you take expectation. So what you get here, xt prime beta, and this thing get cancels. So you get beta. So that's what expectation. Similarly, you can show that expectation of sigma hat is equal to sigma. That means this sigma hat is an unbiased estimator because I have adjusted here. If you don't adjust, you will be simply writing n minus p here. Okay. But we are not doing that, because what we are doing is we are subtracting kp plus 1 from there. So that is why you get this particular one, because you are estimating those many parameters. So essentially what we have is expected value of sigma hat is equal to sigma, and we can also show that these are uncorrelated, and covariance of this beta hat. Now covariance of beta hat vec beta hat is given by this expression. If you remember in your least square theory, the variance covariance, for example, in your simple linear regression, say for example, in y equal to x beta plus epsilon, in this beta hat is x prime x inverse x prime y, and then we have seen that variance of beta hat is sigma square x prime x inverse, right? This is, I am talking about the case when this is normal, I mean this is not necessarily normal, epsilon is 0 sigma square I. Okay, this is n by 1, this is n by p, and this is p by 1, this is n by 1. So you have this. So we have the similar thing here, but what happens that now this has become matrices. So accordingly, you need to actually get the corresponding formula, and that turns out to be this. So covariance of this is this. Actually, I should write it without this hat. I think that was a mistake. Because we have computed the covariance. So this will turn out to be an estimated covariance. Okay, this will turn out to be an estimated covariance. So we'll omit the proof. Now, what about the likelihood? So if you are talking about the likelihood, then I have to make an assumption that ZT follows normal distribution or any other distribution, but we go with the normal distribution. So if you go for the normal distribution, we can write down the likelihood in this particular manner. Likelihood means I will be writing the likelihood corresponding to this. So yt prime minus xt prime beta, that is my zt prime, and z is normal with mean 0 sigma. Therefore, I will be able to write down the corresponding likelihood like this. Some constant minus n minus p by 2 log of absolute of sigma minus 1 by 2 s beta. Now, this is the likelihood. Now, what is this S beta? S beta is same as this trace of y minus x beta sigma inverse y minus x beta. Remember that these are not, I have actually this y, when I consider it's a matrix. See, y is a n by n minus p by k matrix. Okay, so you have to be careful about that. We are not talking about a particular vector. All the vectors put together, so that form a matrix. Because each of the component is a vector, I am putting them together. So the likelihood is given by this, and maximization of the likelihood is same as minimization of S beta. So maximizing the likelihood over beta is equivalent to minimize S beta, and minimization of S beta will actually give me this estimator. So I'll get the same estimator here. So it's same as the least square estimate. Okay. So we'll have the least square means I am talking about GLS, because in this case 6ZT has mean variance sigma. If variance sigma replaced by I, it is same as OLS. So in general it is GLS. So I'll get the maximum likelihood estimator as that of the GLS. Now, another important, so this is part of the estimation. Now, of course, one can talk about the Bayesian estimation in this context, which is little more involved. If you have learned Bayesian, you can see that here what we are trying to estimate, we are trying to estimate. So just I give you the very basic of this Bayesian thing. So in this context, I am trying to estimate. So we estimate, so you have basically, we are trying to estimate beta. Okay, so I will have to have a prior for beta. So maybe I'll take it as n beta naught sigma beta. And then I will have a prior for sigma. That sigma which is corresponding to that. So I'll take a multivariate gamma here and then compute the posterior of this, like the posterior of what? So you get beta given, sigma I will fix it actually at the whatever it is, and then the data. So this is what we'll try to find in this context. Now this is quite involved, so we don't proceed the Bayesian estimation here. But because the notation itself is clumsy, and then practically also it is difficult for you to get into that mode. So we are not going for the Bayesian estimation of VAR model, but maybe if you are going for higher level learning, you can think of it. And now that you know the theory, it's not that difficult because you have learned the Bayesian. So it is something like this. You have a normal mu sigma square, and I want to estimate mu in a Bayesian context. So I'll go for the prior for this. You get a prior of this mu and sigma square. It could be prior of mu into prior of sigma square, and then get the posterior. So I'll get the posterior as p of mu sigma square given the data as p of this given mu sigma square and pi of mu sigma square and integral d of mu sigma square. So this is what the Bayesian. I mean, it's very easy to say this, but actually while computing, you have to go through the whole exercise. So this is what the Bayesian estimate. Now, as I told you, we are not getting into the Bayesian estimate, so I stopped. So we have least square estimate, generalized least square and least square. Generalized least square assume, don't make any assumption. Least square assume that you have sigma is nothing but I, that means ZT has a variance covariance matrix I, and we estimate by generalized least square, and the maximum likelihood we consider the normal, so it just same as the GLS. Now the next problem in this context of where is the order selection, because we are saying so it's like we have, so for example, we have YT is phi naught plus phi 1 YT minus 1. All these are vectors, okay? So remember that this is also a vector. This is a matrix plus etc. plus phi p YT minus p. Now, what should be p? This problem is not new. What should be p? This problem we have addressed in the case of univariate time series. So what was the method that we have assumed? Now in the case of AR model, we could actually look at, if it is AR, we could look at PACF and then get the AR order from that. Or if it is a ARMA, we were doing some kind of, trial and error. Because we don't have so several model we consider and then go for some kind of AIC, BIC criteria to pick up a model. So this is done in the context of univariate case. Now we are going to do the same thing in the context of multivariate case as well. So in order to determine the order P, but here there is another method that we use because of the complexity over here. Looking at PACF plots are not very easy, and even computation of the PACF plots are not very easy. In fact, there are difficulties in the definition itself. So we don't get into that. Rather, we get into what is known as likelihood ratio procedure, so or sequential likelihood ratio test approach. So in this what we do is that compare where L model with where L minus 1 model, or in other words we test the hypothesis that phi L equal to 0 versus phi L not equal to 0. What is this L? That means the coefficient at the Lth stage. So that is what we are doing. So if you look at the where, you can see that. So I have written here. So for example, I'll just assume if I'm going for the pth order, I'll test the hypothesis that whether this phi p equal to 0 against that phi p minus 1. So phi p minus 1 is my interest. So up to phi p minus 1 we are considering. That is something, we have to assume. So up to phi p minus 1 I am considering, and then we are worried about what happens to the pth order, the pth point. So that is what, so P is, of course, this is L equal to 1, 2, etc. So you can think of 1, 2, 3, etc. Keep on doing that. Sequential means I'll do at every stage to the next one. This stage to the next one. This stage to the next one. So that is why it is called sequential. So PL equal to 0 versus PL not equal to 0 using the likelihood ratio. So what is the likelihood ratio here? The likelihood ratio is, you know that the likelihood is basically, we consider this likelihood with L minus 1 and likelihood with L. And sigma is of course a fixed quantity. And then I'll consider this, maximize this likelihood, consider this likelihood ratio. Now, if you this is just a notation to indicate that you are considering this is because actually, you know, when you consider this likelihood, this sigma basically comes in the denominator, so this role is getting ulta, or it goes up, and then n minus L by 2. So I'll get this kind of an expression for lambda, the likelihood ratio. And the test procedure is to reject for large values of this minus 2 log lambda you will consider, which can be written like this. Now we don't generally consider this directly because this is adjusted for some bias. And then what we consider is this quantity. Same thing, I mean like this quantity, but instead of multiplying with this, we consider multiplying with this quantity instead of n minus L, sorry. Instead of just minus n minus L, we consider sorry, think, yeah, minus L n minus L minus 1.5 minus KL, this quantity we consider. This I told you that this is basically for the bias correction, so you don't have to worry too much about this, why it is done this. So a commonly used test statistic, because even if you write this, you are right. Only thing is that this approximation is not very good to chi-square, so you correct the bias by adjusting this, and then you get this is much better, and that is proved in 2003 or 2005 by Say and somebody else. So this is proved to be a chi-square with chi-square random variable with k-square degrees of freedom. So what is needed is that examine the test sequentially starting with L equal to 1. That's what I told you just a minute before. You start with L equal to 1 and L equal to 0. So L equal to 0 essentially means that you are not going to consider any of the past values for prediction. So that's what L equal to 1 against L equal to 0, then L equal to 2 against L equal to 1, L equal to 3 against L equal to 2, etc. So if all p values ML test statistics are greater than the specified type 1 error for L greater than p. So from p onwards, if you know you reject the hypothesis for all these things, then the var p model is specified. This is so because the test rejects the null hypothesis but fails to reject all these things for L greater than p. Okay, oh, there is a bracket missing here. So this is because the test rejected the null hypothesis, this is equal to 0, but failed to reject all these things for L greater than p. I reject means fail to reject. So reject means this is not 0, so it is equal to 0. That's what fail to reject means, it is equal to 0 for L greater than P. So L greater than P, you get all of them 0. So we will consider the VRP model in such a case. Okay, the bracket is missing here. So one generally start with a smaller value of P. That may, I mean, I would like to start with 2 or 3, and then you can consider, especially when K is large. This is one criteria, what is called as sequential likelihood ratio criteria. Another criteria that we use, you all know that the information criteria, where the information under the normality assumption. Again, information criteria uses the likelihood, and likelihood uses the distributional assumption. So you have to have VAR model with normality assumption. So in such a case, AIC, BIC, and HQZ, Han and Quinn, this can be computed in this particular manner. I should write HQC, Han and Quinn information criteria. So these are 3 different criteria. Of course, there are a couple of more criteria one can define. And under normality case, this is the expression. You can see that the first term are same for all information criteria, which is nothing but the goodness of it to the data, because this is basically correspond to the goodness of it of the model to the data, which is nothing but the maximized likelihood. Second term is basically a penalized thing or penalty. Now this penalty is basically how the penalty for the complexity of the model. So what happens that the likelihood increases as your number of parameters increases. But what happens that if you don't keep on increasing, there is no point that you will get a model which is good, because you keep on increasing the parameter, model will be better and better and better. So we penalize that, and the penalty is given by this particular term. So different types of penalties being used. AIC, you have this type of penalty. BIC is this, and Hankin criteria, you have this. So here, whereas the second component penalizes more heavily on complicated models. Now you can use two commands here, var order or var order I, to determine in R. So just give, it's pretty simple, var order, and if you just put var order X of the matrix that you, or the vector that you have for the data, it will identify the order in just one command, and you will get the corresponding things. So of course, I suggest you to look at our textbook with R for a worked out example, so that you can see them here. So now this is the way that order is determined, and how the model checking is done. And as you know, the model checking is done by residual cross correlations. So now what happened, that the model that you have actually proposed should capture the cross correlations. So we will check it with gamma L hat, which is the residual cross correlations. So if the model is correct, the residual cross correlation will match with, sigma, or if you can multiply with the sigma, that it will become I. So what we have is, this is what the covariance matrix corresponding to that. Now so the I is here, I'm bringing that I over here. So you actually do little bit of rewriting here. This already we have seen. So I'm trying to find the Lth order or lag L covariance, and that can be written like this. Now instead of the covariance, you can also actually consider the correlation, the lag L correlation matrix, and then see that whether they are significant. So correlation matrix, this we have seen in the case of VAR model, the correlation matrix is computed in using this formula. Now what is this? This will be gamma 0 d hat. D hat will be variance, this covariance divided by square root of the variance. So I will have diagonal of gamma hat 0 comes as D matrix. So this formula we have seen when we introduce the correlation matrices in the case of VAR models. Now you can actually use, instead of, see, plotting is a bit difficult in this context because there are cross correlations, and the order is not just like in the univariate case. Univariate case we do the plotting, but that is a bit difficult. So we have, in univariate case, if you remember, we have Lee and McLeod test, or there is LQ, Lingbox test. And now we have already introduced the multivariate version of Lingbox and Lee and McLeod test. So you can use them in this context. So these are called multivariate portmanteau test. So that can be used over here to test the order. Now we get into the last part of this lecture, which is prediction. So what is prediction here? How is the forecasting done? Now in the case of AR model, the forecasting is pretty simple, because you can just go for a recursive forecast. So here I am assuming, suppose I have a k-dimensional VAR-P model, which is like this, and this is the information available at the time point t. That means I have the information about all xt's. Some terminologies: forecast origin, forecast horizon, S-step predictor. These are known to you because forecast origin is at time t, you are now trying to pick a forecast. Forecast horizon, how much point ahead that you are trying to make the forecast. So H is the forecast horizon, forecast origin is t, and H step predictor means you are computing xt plus h, a predictor for xt plus h. Now we know that the minimum MSE forecast is given by the conditional expectation. So this is given by, this T notation stands for conditional on T. So I am denoting it by this quantity, xt plus h given omega t. And in the case of linear, it's very easy to compute this, because not linear, in the VAR model, because what happens that you can write it t plus 1 here, so that this will be t, t minus 1, etc., and all these are known, including t is known, so all this becomes 0. This will continue there, this becomes 0, and then it remains here. So you will get an expression, t plus 1 means nu plus a1 x. This t stands for conditional on omega t. So xt, because h is equal to 1, t minus 1, t minus 2, etc., t minus p. So it's very easy. I mean, once these a1, a2 are known and nu is known, then you get prediction one step. And from one step, you go for two step. So the above formula can be recursively used for computing h-step predictor starting with h equal to 1. So the h-step predictor formula is given by this. So this is the, how did I arrive at this? So I substituted this here. You get, you can substitute, because in the case of, this is a1 plus a2, etc. So you will get those terms, picking those terms over here, you get this kind of an expression. So this is in the case of var1, okay, whereas this is general var p, so don't get confused. I mean, for var1 process, this reduces to this. This we have done in the case of univariate time series, 1 plus phi1 plus etc. phi1 to the power of h minus 1 nu plus phi1 xt. So, okay, so same thing. Now, this is an exercise where I have given you a var1 model. I have given you xt, new value is given, a is given. So I asked you to compute one-step predictor. I also asked you to compute two-step predictor. Now, two-step predictor may require this. Okay, so how do you get into that? You simply write t plus 1 here. So this will become t, and xt is available to you, a is available to you, and take expectation of this. So this will go to 0, nu is available. So you get the answer. So that is et xt plus 1. Now to xt plus 2, you write t plus 2 here. So this will become, if you write t plus 2, then this will become t plus 2 minus 1. So that will be t plus 1. Now you already obtained an answer for t plus 1. Substitute here, you have the answer. Okay, do the same thing for var2. Here I have only one term, here I have two terms. So do this numerical application in this case. Now I have a data analysis exercise. This all of you should submit. So get the data on investment, income and consumption for 10 years. Probably Indian data, or you can get it from any other country as well. Now plot this data, obtain the sample ACF, obtain the time series plots of, now when I say 10 years, it is not yearly, mostly these data are quarterly. So you should be able to have about 40 points. Now if it is yearly, try to get little more, about 20-25 observations, because otherwise, you know, these predictions and other things will not be good. So what I want you to find out an appropriate var model. How do you get that? Using the order selection procedure. So suggest a var model and then predict for next 8 quarters. Okay, so that's about this today's lecture. Thank you.